And up next is our final technical talk for the 22nd Annual CERIAS Security Symposium. David Tian, Assistant Professor in Computer Science, whose work is primarily in system security, and is a member of the PERSEC laboratory here at Purdue. His research involves embedded systems, operating systems, and trusted confidential computing. Professor Tian, it's all yours.
Hello, can you guys hear me? Okay, hello?
Loud and clear, looking good.
Yes, we can hear you.
Okay, somehow I could not start my video. Okay. There's very good access control here. I cannot start my video by myself. Very good. Okay, let me try to share screen. Oh. This is not good because I need to authorize Zoom to share the screen. All right. Let's see if I can do this very quick.
David, don't feel pressed. We have a few minutes built in here. We're actually a couple of minutes
okay.
schedule.
Okay, so apologize.
Yeah, no. So while you're working on that, I'm going to use it as an opportunity to make some announcements. So we have this technical talk, and then following, let me turn my video on. This technical talk, and then following this technical talk, we'll conclude the symposium with the closing keynote address, which also serves as this week's CERIAS Security Seminar. So here's your commercial for that. So weekly throughout the academic year, on Wednesdays at 4:30 Eastern, we host the CERIAS Security Seminar. So weekly, we have somebody from industry give a talk, and it is actually a 4-credit class here at Purdue. So there is a number of students who are enrolled. It's a graduate level lecture class. Then during the summer, we've been hosting these as well, but just not at 4:30. So while I know that we're going to very much enjoy Amit Jorn from Tenable, who's going to give the talk here in about 20 minutes or so, about a half hour from now, I would encourage you to take a look every Wednesday at our website for the Zoom login for the weekly security seminar. Dave, are you in a good position now?
Yeah, I think so. Can everyone see my screen?
We can, and your slides. Great. It is all yours, Dave.
Awesome. Sorry about this. Somehow, like every time when I update my Mac, I have to, authorize Zoom to share the screen. All right. With further ado, let's get started. So all credits goes to students, and as usual, professors just talk like what I'm doing right now. So my topic today is about building an MMIO-based security reference monitor for unmanned vehicles, for example, such as drones. And if you look at typical embedded systems or cyber physical system, we pretty much can abstract the whole system in 2 parts. On the top, we have the whole software stack. For example, you could have a user space task. You could have a real-time operating system. And in the bottom, you could have different peripherals attached to the system to achieve some goals. For example, you could have SPI I2C, you could have CAN bus connect ECUs, you could have Wi-Fi, you could have timers as well. And if you look at the attack surface, pretty much, attackers could attack the whole system from 2 perspectives. For example, attackers could try to compromise a task, and then from that task, attackers is able to compromise the whole real-time operating system. Or attackers could launch physical attacks from peripherals. For example, attackers could try to do CAN bus masquerading, or attackers could just do spoofing attacks against certain bus within the system. And if we look at the MMIO layer, which is short for memory mapped IO, in a typical embedded system, we realize all communications go through MMIO. This is especially true for cyber physical system, because in the end, the purpose of a system is to impact the physical world. And to do that, you really need to do some IO operations. And we also realized, in these systems, it's common to have real-time operating system or real-time operations. And these operations exhibit deterministic patterns. Again, if we think about, typical embedded systems or cyber-physical systems, they are fairly simple. They are power constrained. They do not have like super crazy computation power like, typical laptops we are using nowadays. They are programmed to do probably just a few things, but they do it very well, and they are deterministic. And that's the reason why we're able to see this deterministic pattern within the system. And based on this intuition, we realized maybe we're able to attack malicious activities within the system by looking at anomalies happened at the MMIO layer, which is memory mapped IO level. For example, this figure shows the difference between typical or normal GPS operation and GPS spoofing attacks. So as you can see, like, when GPS is under attack, you are able to see a higher count of ephemeral messages in case of spoofing. Again, this is also intuitive, right? Because if you really want to launch a GPS spoofing attack, you cannot use just one message to redirect your drone to a destination. You have to keep sending messages until you're able to continually redirect the drone to the destination. I mean, this is the reason why you are able to see higher count of GPS messages. And essentially, we look at a number of attacks within the domain of cyber-physical system. For example, we look at timer attack, RAQ override, CAN bus masquerading, and we try to put them into a different categorizations. For example, for different attacks, we might have different defenses which can defend against these attacks. We have crypto, we have compartmentalization, we have fingerprinting, and we have physical modeling approaches. And we also try to record the IO level anomalies for each attack. As shown in this figure, we have different attacks, we have different defenses. But if you look at all these defenses, none of them can defend all these attacks. But meanwhile, if you look at all these attacks, all of them reflect some anomaly at the IO level. So which gives us the motivation to build an IO reference monitor for unmanned vehicles. And essentially, this is what we did. We built M2MON, which is a MMIO-based security reference monitor. To call it a security reference monitor, you have to specify 3 properties. So first, the reference monitor has to be tamper-proof. For example, if you deploy the security solution in your drones, then attackers cannot compromise the system. This means whenever attacks happen, our reference monitor is able to capture that. The second property is called complete mediation, right? We want to make sure like we are able to capture each attack and no one can bypass our reference monitor. And the last one would be verifiable. Ideally, for any security solutions, we want a formal verification. But even if that is hard to achieve, we want to make sure the whole code base is small enough so that we're able to even manually verify what's going on with the system. So if we look at the design challenges within a typical embedded system, again, this is a very sad story, because if you look at embedded system and comparing to the typical system we're using from laptops and desktops, embedded systems are doomed in a certain way. So for example, this is a typical figure of an embedded system. Again, CPU probably could have multiple privilege rings. For example, you could have unprivileged mode, you could have privileged mode. But unlike typical system, embedded system developers would try to put everything into privilege mode. Again, for performance, because no one can afford the overhead of context switching between user mode and kernel mode. And even worse, things or the typical security hardware features we take for granted, like a memory management unit, are not available within embedded system. The best you could have probably is just a memory protection unit rather than a full-fledged MMIO. All right, so if you look at this figure, we have everything grouped together within the privilege mode. Task libraries, real-time operating system drivers, interrupt service routines. This means any of the layer compromised, the whole system compromised. Now, the research challenge is how could we design a security reference monitor and put it somewhere so that we're able to, first of all, tamper-proof from different attacks. Second of all, provide complete mediation and hopefully verify. And even worse, if you dive into these different peripherals like GPS or different sensors, they are essentially another embedded system with their own software stacks running inside. So let's take a look at our naive approach, because if you look at the second property of a reference monitor, which is the tamper-proof, the complete mediation, intuitively, we want to put our reference monitor as low as possible so that it is able to capture all the accesses to peripherals. And that is what we did in our first design, where we just put the M2MON microkernel at the very bottom of the software stack so that all the upper layers have to go through this microkernel to access different peripherals. But what about complete mediation? What about tamper-proofness? Because if any of the layer above compromised, then our M2MON kernel would be compromised. Then this is not a security reference monitor. So we could try something like software fault isolation techniques, for example, applying data flow integrity or control flow integrity within the runtime to isolate all these upper layers within the system. But the problem is also obvious because, there's lagging. The problem of this solution is also obvious because all these SFI approaches introduce a lot of runtime overhead, which is forbidden for real-time and most embedded systems. So can we do better? So we realize, okay, if we cannot do software approach, then we need to resort to hardware. In this design, again, we still have the M2MON microkernel with privilege mode, but instead of trying to leverage software-based solution to confine task libraries within the same privilege mode, we try to push all of them outside the privilege mode, so including the real-time operating system, right? So here in this solution, we reserve the privilege mode for our microkernel and push everything outside the privilege mode. This solution is very good because now we have hardware guarantee that none of the software stack within our privilege mode is able to compromise the microkernel within the privilege mode. This is pretty much what we have nowadays within a typical laptop or desktop, where you have kernel code running in Ring 0 and you have all user space stuff running in Ring 3. All right. And again, this approach still satisfies the complete mediation because for drivers, if they want to access different peripherals, they have to go through the M2MON microkernel. And the way we enforce the access control is to use the memory protection unit available within embedded. But what about interrupt? Because one thing we realize is if we push out interrupt within the user space, within the unprivileged mode, we're gonna introduce a lot of overhead because whenever interrupt happens, we have to go back to the user space and then do something there and get back to the kernel space. So again, even though we're using hardware features to protect M2MON, but we inevitably introduce a lot of runtime overhead. So to deal with that, we realize, okay, let's bring interrupt service routine back to the privilege mode. All right, so this is our solution. But then the problem is, how can we trust the interrupt service routine? What if they got compromised? Because these routines are not written by ourselves. These routines are provided by, let's say, real-time operating system or even application developers. Our solution is simple. We apply SSI to ISR here. So the difference here is instead of applying this software fault isolation techniques to all the user space software stacks, we only apply this technique to the interrupt handler so that we're able to minimize the overhead introduced by software fault isolation techniques. Now, with this design, we're able to achieve non-bypassable, which means there's no attack that can bypass the monitoring of M2MON microkernel. And it's tamper-proof because we have a dedicated CPU RAM reserved for M2MON microkernel. And hopefully it's verifiable. And in the end, M2MON has only hundreds of lines of code compared to like much more for a typical real-time operating system implementation. And once we have M2MON microkernel, and you can imagine we're able to build different applications using that to achieve or to defend all those attacks we have seen earlier. So for example, we could implement common filter within M2MON microkernel so that even if the real-time operating system is compromised by attackers, the common filter still works, which means the system is able to get the correct sensor values no matter what. Or we could use M2MON to build a MMIO access pattern firewall. And we could use access frequency, access chain, or access list to regulate the MMIO access pattern within the system. And if we see any anomalies, we're able to fire an alarm accordingly. So we evaluate our system on two popular drone platforms, and we consider both performance evaluation and the security evaluation. Now, if you look at the performance evaluation, we just run the benchmarks available within this drone platform. And we look at the deadline because we're dealing with real-time systems. And in most cases, if we look at the rate of M2MON, it's minimum, and we do not violate any deadline except one application which is called one HC loop. But if you look at the violation there, even the baseline, which is the not modified drone system, violates that deadline. But the good news is, other than that, M2MON does not violate any real-time deadline. And the average runtime overhead is less than 10%. And if you look at the security evaluation, if you recall all those cyber physical attacks we have surveyed earlier, now we're able to defend against all of them using a typical firewall to regulate the MMIO access pattern. We could use access list, for example, like what MMIO addresses the system would regularly read, or we could use access frequency. For example, if we're able to observe more messages like GPS ephemeris messages, then we could fire an alarm, or we could use common filter to do sensor value fusion to make sure the system can receive a correct sensor value. All right. And one example is this timer attack. So for example, attackers could try to change the system timer to do something, for example, to change the schedule of a certain task, or just to delay some real-time task. And if we look at this attack, if we look at the system, we realize this timer is only set up when the system is boot. And after that, this timer should not be accessed by anything. And to defend against this timer attacks is trivial. And all we need is to write a policy within M2MON microkernel saying that, after system boot, we won't allow anyone to access this timer. That's it. Then we're able to defend against this, typical timer attack. For sure, this system also has some limitations. And one thing we realize is, especially if you look at this firewall implementation, we allow users to load different policies to regulate MMIO access patterns. And one intuitive question we would like to ask is, how skilled this system would be if we allow users to load a number of policies, right? And turns out this is application dependent. So for example, if you look at this auto trim application on this audio pilot drone platform, the overhead is kind of linear, right? But if you look at like the other two, like for example, for example, this update battery compass, it look like exponential, especially after we have around 100 rules within the system, the overhead is huge. All right, so this is like something we really need to solve in the future, because in the end, if we really want to scale the whole system, we really need to find a more efficient way to do this kind of like MMO access pattern filtering. Anyway, here's the conclusion. We realize a lot of attacks happen within this embedded system or cyber physical system would require certain access of MMIO access pattern. And this pattern would reflect some anomalies when the system is under attack. And we built a security reference monitor for the MMIO layer so that we're able to capture all these attacks. And we evaluate on two popular drone platforms. We show that we're able to defend against all these attacks with a reasonable runtime overhead. All right, thank you. This is the email address of my student. I'm here to take questions. I'm not sure if I run out of time or we have more time.
We do have some time. So if there are some questions, please drop them in the Q&A. There was a request that did come in to the moderator or to the panelists asking if your slides and some of the slides of the other presenters would be available. I did drop that information in the chat side, but I will share here that all of the sessions, all of the proceedings from this symposium are being recorded, and those recordings will be available from both the CERIAS website as well as our YouTube channel. And those, at least on our website, will have the accompanying slides with them. Interestingly, you can view the symposium proceedings for, I think, all 22 of our individual symposiums on our website, as well as our weekly security seminars dating back to at least 1999. I've often pointed out that the list of speakers at the weekly security seminar, as well as their symposium, reads like a who's who in the cybersecurity industry. Both people who are huge names within the industry at the time of their speaking, but also those who are very young in their career who have gone on to have extremely established and groundbreaking careers within cybersecurity. Dave, I think you are off the hook. No Q&A come in. I appreciate your presentation this afternoon and all that you and your lab mates are doing in the PERSEC laboratory.